Okay, so now we put the two together and start doing our analysis by looking with respect to series and parallel circuits and how we analyze them with the combinations of both series and parallel RL circuits. So again, best way to look at this, let's take a look at an example. Determine the total current and the phase angle in the circuit below. Draw a phasor diagram showing the relationship to the source voltage and total current. So we're going to take a look at this. Again, we're going to have to start by converting our inductor into an inductive reactance, and then we can do our analysis. We're given the source voltage 10 volts and a frequency of 1.5 kHz. So the inductive reactance calculated comes out to 1.41 k ohms. The inductive susceptance, then, when we invert that x sub L, we get 709 microsiemens. The conductance magnitude based on the resistor value 2.2 k ohms inverted gives us 455 microsiemens. So the total admittance then is the vector sum here in rectangular form, Y total, G minus J BL, 455 microsiemens minus J, 709 microsiemens. So from that, we do our polar conversion using the relationship, and we end up with 842 at an angle of minus 57.3 microsiemens. So there's our phase angle. We can then use Ohm's law to determine the total current. I total then is equal to the source voltage times the admittance total, and using the phasor polar form here, then 10 times 842 gives us 8.42 and a angle of minus 57.3 milliamps. The magnitude of the total current 8.42 milliamps then, and it lags the applied voltage by 57.3 degrees as indicated. The phasor diagram then we can see below the source voltage 10 volts on the x-axis, and then the total current of 842 milliamps at an angle of minus 57 degrees. Another example here, again we can see we've got a compound series parallel with a resistor and an inductor, resistor and an inductor. So what we do is we calculate for the series branch, we calculate for the parallel branch, and then we combine them together in series. So go ahead and pull out your calculator, go through these calculations, calculate each of the conversions here to a inductive reactance, put it in rectangular form, do an inverse to get your conductance, calculate your total susceptance, do an invert, and then put them together and convert them. Same thing here. Again, we've got two two branches here, one series, one parallel. Combine the parallel branch with the series branch into a total series branch and calculate I total. Finally, in this one, we've got two series branches in parallel, both of them given as values in henries. So you can, again, pull out your calculator, run through this step by step. It's pretty easy. You should have it down by now on how to do this. Give you good practice. Another one, same type of relationship. Same thing. We've got henries and henries. They want us to calculate the voltage across each element. In this case, draw a phasor diagram and a current phasor diagram. So we determine the current through each branch. And from that, then we can calculate the voltage drop across R1, L1, R2, and L2 just by applying Ohm's law. It's not that difficult. It looks difficult, but it's not. It's just several steps. So again, pull out your calculator, do the calculations here. Determine the voltage across each element, draw the phasor diagram. Well, here you go. Here's each of the voltage drops. V across L2, V across L1, V across R1, R2, and then of course the source and each of the angles. Over here we can see then the source, the current through 2, the current through 1, and each of the angles that are presented. Okay, so you've got a good idea how to do this. Take some time, work through them, spend a concerted and conscious amount of time working through these problems, and you should be okay.